Imagine if scientists reconstructed Earth's history from rock layers and isotopic signatures spanning 4.6 billion years. Every page tells a story more insane than the last, from the time our planet was basically a lava lamp the size of a world, to when oxygen was literally poison to most life forms. Scientists in 2025 have been rewriting this story with groundbreaking discoveries that reveal how close we came to never existing at all. There were 5 major mass extinction events when life almost got completely erased from the rock record, and somehow we're still here to tell the tale. But this story starts in a place you wouldn't even recognize as Earth. When Earth was a literal hell planet. 4.5 billion years ago, our planet looked nothing like the blue marble we see in space photos today. Earth was basically Venus with commitment issues, a molten hellscape where surface temperatures hit 2,000 degrees Fahrenheit on a cool day. The entire planet was covered in an ocean of liquid rock that stretched from what would eventually become continents to the deepest ocean basins. This wasn't just hot, this was metal melting, atmosphere boiling, everything is on fire hot. Advanced computer modeling from 2025 research teams has shown us exactly what this nightmare looked like. For the first half-billion years of Earth's existence, the surface never cooled enough to form solid rock consistently, with limited rock preservation and intense heat dominating the early Hadean period. Continental crust began solidifying during the Archaean Eon as conditions gradually stabilized. The whole planet was essentially a giant lava lamp, with currents of molten material flowing in slow-motion rivers of fire. Massive impacts from asteroids and comets kept heating things up, adding more energy to a system that was already running at maximum temperature. Each collision sent shockwaves through the molten surface, creating temporary craters that filled back in with liquid rock within hours. If you somehow managed to time travel to this period, you wouldn't just die from the heat. The atmosphere was a toxic soup of methane, ammonia, hydrogen sulfide, and carbon dioxide that would be toxic to most life forms we know today. There was no oxygen anywhere on the planet. The atmospheric pressure was probably dozens of times higher than what we experience today, creating a crushing environment that makes Venus look hospitable. Water vapor existed in the atmosphere, but it couldn't condense into liquid because the surface temperature was too high. Any droplet that tried to form would instantly turn back into steam. This chemical cocktail wasn't just dangerous, it was completely alien. The methane and ammonia created a reducing atmosphere that worked like a massive chemistry set running wild experiments. Ultraviolet radiation from the young sun, which was about 30% dimmer than today but still intense enough to drive chemical reactions, bombarded the surface during the early Archaean period when no ozone layer existed to filter it out. Lightning storms probably raged constantly through the thick atmosphere, providing energy for molecular interactions that wouldn't be possible under normal conditions. The strangest part is how impossible it seems that anything could emerge from this chaos. Early Earth was basically a planetary-scale furnace with a toxic atmosphere and no solid ground anywhere. Every condition that we associate with life was completely absent. There were no stable surfaces for complex molecules to organize themselves, no liquid water for chemical reactions to take place in controlled environments, and no protection from radiation or impacts. The planet was essentially sterilizing itself continuously. But recent discoveries have revealed something remarkable hiding in this hellscape. Zircon crystals found in Australia and dated to this early period contain chemical signatures that suggest liquid water existed somewhere on Earth even during the molten phase. These crystals are virtually indestructible, and they preserve chemical information about the conditions when they formed. The isotope ratios in these ancient zircons indicate that water was interacting with rock at temperatures low enough for the water to remain liquid, at least in some locations. This discovery has changed how scientists think about early Earth conditions. The planet wasn't uniformly molten everywhere at all times. There were probably areas where the surface had cooled enough for water to exist, maybe in shadowed regions or at higher altitudes where atmospheric pressure was lower. These would have been tiny islands of relatively stable conditions in a world dominated by chaos. The water would have been incredibly hot by our standards, probably close to boiling, but it was liquid water nonetheless. The atmosphere during this period was like a chemistry experiment designed by someone who wanted to see what would happen if you mixed every reactive gas together and then added heat and electricity. Methane and ammonia don't just sit quietly in the atmosphere, they react with each other and with other compounds to create more complex molecules. The constant lightning and ultraviolet radiation provided energy for these reactions, while the high pressure kept everything compressed together. This wasn't a stable, peaceful environment, but it was incredibly active chemically. New research from 2025 has revealed that asteroid bombardment during this period wasn't just destructive, it was also creative. Each impact brought new chemical compounds to Earth's surface and atmosphere. Some asteroids contained organic compounds that had formed in the cold depths of space, while others carried metals and minerals that became part of Earth's chemical inventory. The impacts also created temporary high-energy environments where complex chemical reactions could take place. Instead of just destroying everything, the bombardment was actually delivering raw materials and energy for building more complex molecules. The heat and pressure from impacts created conditions similar to what chemists use in laboratories to synthesize organic compounds. High temperature and pressure can force simple molecules like methane and ammonia to combine into more complex structures. The shock waves from impacts created areas of extreme conditions that lasted for seconds or minutes, just long enough for chemical reactions to create new compounds that wouldn't form under normal conditions. These reactions were probably happening millions of times across the planet's surface, as impacts continued to reshape the landscape. What makes this period even more fascinating is how the constant destruction and recreation actually helped complex chemistry develop. Every time an impact melted and reformed part of the surface, it mixed different chemical compounds together in new combinations. The planet was essentially running countless chemical experiments simultaneously, trying out different molecular combinations to see what would stick around long enough to become more complex. Most of these experiments failed, but the few that succeeded began the long process of building the molecular machinery that would eventually become life. This hellish environment that should have prevented any complex chemistry from developing somehow became the perfect laboratory for creating the first organic molecules. The combination of high energy from impacts and volcanic activity, a chemically rich atmosphere, and the presence of liquid water in protected areas created conditions where simple molecules could combine into more complex structures. The constant mixing and heating ensured that different compounds would encounter each other and have enough energy to react. What looked like a recipe for sterility turned out to be exactly what was needed to jumpstart the chemistry of life. But the real surprises were still coming, and they would involve something that seems completely harmless to us today. The Great Oxygen Poisoning. Here's the thing nobody tells you about oxygen. It was Earth's first weapon of mass destruction. Around 2.4 billion years ago, during the early Proterozoic Aeon, tiny blue-green bacteria called Cyanobacteria started doing something that would make them the most successful environmental terrorists in planetary history. They began photosynthesis, which sounds innocent enough until you realize they were pumping a highly toxic gas called oxygen into an atmosphere where it had never existed in significant amounts before. These cyanobacteria were the first organisms that figured out how to use sunlight to make energy, but their waste product was pure poison to almost everything else alive at the time. The early Earth had been a comfortable place for anaerobic life forms, organisms that not only didn't need oxygen but were actively harmed by it. For billions of years, life had evolved in an oxygen-free world where methane, ammonia, and hydrogen dominated the atmosphere. Suddenly, these microscopic troublemakers started flooding the environment with a gas that was chemically reactive enough to destroy the cellular machinery that most life forms depended on. The scale of this disaster becomes clear when you look at 2025 isotope studies of ancient rock formations. These studies analyze different forms of carbon that get preserved in rocks, and they reveal the proportions of living things that existed during different time periods. The data shows that oxygenation drove mass turnovers among anaerobic life during what scientists call the Great Oxidation Event. Many early anaerobes vanished as oxygen-tolerant lineages emerged to dominate the new atmospheric conditions. This wasn't a gradual decline over millions of years. This was biological warfare on a planetary scale. To understand how catastrophic this was, imagine if aliens showed up tomorrow and started replacing all the air in your house with chlorine gas. That's essentially what happened to the anaerobic organisms that had been running Earth's ecosystems for billions of years. Oxygen is incredibly reactive, which means it bonds aggressively with other molecules and breaks them apart. For organisms that had never encountered this gas before, exposure to oxygen was like being chemically burned from the inside out. Their proteins got oxidized, their cell membranes fell apart, and their DNA got shredded by oxygen-free radicals. The Great Oxidation Event nearly ended life before it really began. The planet had spent billions of years developing complex ecosystems based on anaerobic metabolism, and suddenly the fundamental chemistry of the atmosphere changed completely. Most of the bacterial communities that had colonized the early oceans simply couldn't adapt fast enough. They had no evolutionary experience with oxygen, no protective mechanisms, and no way to repair the damage that this new gas was causing to their cellular structures. The few survivors had to literally hide in oxygen-free zones to avoid being chemically burned alive. These organisms retreated to the deepest parts of the ocean, buried themselves in sediments, or found other places where oxygen concentrations remained low enough for them to survive. They became refugees in their own world, pushed into marginal environments by the toxic waste products of photosynthetic bacteria. Recent discoveries have revealed ancient rock formations that scientists call oxygen refuges, geological structures that preserved anaerobic life during this period of atmospheric transformation. These refuges were like underground bunkers where oxygen-sensitive organisms could wait out the chemical apocalypse happening on the surface. The refuges were found in deep ocean environments and within specific rock formations that acted as barriers against the oxygen-rich atmosphere. Some of these refuges preserved communities of anaerobic bacteria that survived for millions of years, while the rest of the planet's atmosphere became increasingly toxic to their way of life. New research from 2025 shows that some organisms managed to develop what were essentially the first gas masks in Earth's history. These were protective cell walls and chemical defense systems that could neutralize oxygen before it damaged vital cellular components. Some bacteria evolved thick protective layers that prevented oxygen from reaching their sensitive internal machinery. Others developed chemical compounds that could soak up oxygen molecules and render them harmless. These early protective mechanisms were crude, but effective enough to keep some lineages alive during the worst of the oxygen crisis. The organisms that survived this period were either the ones that could hide from oxygen completely or the ones that managed to develop chemical defenses against it. This was evolution under extreme pressure, with natural selection favoring any mutation that provided even slight protection against oxygen toxicity. But the most remarkable survivors were the organisms that learned not just to tolerate oxygen but to use it. Some bacteria developed the ability to harness oxygen for cellular respiration, turning the toxic waste product of photosynthesis into a powerful energy source. This was like learning to breathe fire instead of being burned by it. These aerobic organisms discovered that oxygen could be used to extract much more energy from organic molecules than any previous metabolic process. The chemical reactions that use oxygen to break down organic compounds release about 20 times more energy than anaerobic processes. This meant that organisms that could handle oxygen suddenly had access to energy sources that made them incredibly competitive. They could grow faster, reproduce more quickly, and dominate environments where oxygen levels were rising. The gas that had been a planetary poison became the fuel for a new kind of life that was more energetic and complex than anything that had existed before. The Great Oxidation Event also transformed Earth's geology in dramatic ways. Oxygen reacted with iron that had been dissolved in the ancient oceans, creating massive deposits of iron ore that we can still see in rock formations today. The planet basically rusted on a global scale as oxygen bonded with metals and other compounds that had been stable in the previous atmosphere. These banded iron formations are some of the most visible evidence of how completely the Great Oxidation Event changed Earth's chemistry. The cyanobacteria that started this whole disaster also pulled carbon dioxide out of the atmosphere as part of their photosynthetic process. This removed greenhouse gases and caused global temperatures to plummet. The early Proterozoic period became much colder, and there's evidence that the planet may have experienced conditions where ice covered most of the surface. This mass poisoning event that killed most anaerobic life accidentally created the energy-rich atmosphere that would eventually power complex life. But the climate consequences were about to create an even more extreme challenge for the survivors. The same process that had filled the atmosphere with toxic oxygen was now pulling so much heat out of the system that the entire planet was about to become something unrecognizable. Snowball, Earth's frozen apocalypse. Picture Earth as a giant ice cube floating through space, completely frozen from the North Pole to the South Pole with no liquid water anywhere on the surface. This actually happened to our planet, and climate modeling research from 2025 has shown us exactly how extreme these conditions were. Ice sheets stretched over a mile thick at the equator, which means the tropical regions where we expect palm trees and beaches were buried under more ice than currently covers Antarctica. The entire planet looked like a massive snowball drifting through the solar system. The oceans didn't just freeze over with a thin layer of ice like a pond in winter. They turned into solid ice all the way down to the seafloor. The water that makes up most of our planet's surface became a solid mass of frozen material that extended from the surface down to the ocean bottom. Marine life that had been thriving in liquid water suddenly found themselves trapped in a world where their entire habitat had transformed into solid ice. There was no liquid water anywhere on Earth's surface during these events. This planetary deep freeze happened at least twice during Earth's history, between 600 and 800 million years ago during the Neoproterozoic period. Each time it looked like the final game over for life as we know it. Both times, the planet spent millions of years locked in this frozen state. These weren't brief cold snaps that lasted a few thousand years. These were extended periods where Earth remained frozen for longer than humans have existed as a species. The ice sheets reflected sunlight back into space instead of allowing the planet's surface to absorb heat. This created a feedback loop where the more ice that formed, the more sunlight got reflected away, which made the planet even colder and caused more ice to form. It was like the ultimate freezer burn that lasted for millions of years. The planet got stuck in this frozen condition because once the ice reached a certain coverage, it became almost impossible for the sun's energy to warm the surface enough to start melting the ice sheets. Temperature measurements from ice core samples and geological evidence suggest that global average temperatures dropped to around -40 degrees Fahrenheit. The equatorial regions, which today experience temperatures above 80 degrees Fahrenheit, were probably colder than the current Antarctic winter. There was no seasonal variation because the entire planet was locked under ice. No rain fell anywhere because all the water in the atmosphere was frozen. The only precipitation was snow that added more layers to the already massive ice sheets. Life seemed doomed to extinction under these conditions, but recent evidence from 2025 research has revealed that some organisms managed to survive in hot springs under the ice. Volcanic activity continued even during the frozen periods, and this geothermal energy created pockets of liquid water beneath the ice sheets. These underwater hot springs provided refuge for extremophile organisms that could tolerate high temperatures and unusual chemical conditions. The volcanic vents released heat and dissolved minerals that kept small areas of water liquid, even when the rest of the planet was frozen solid. These volcanic oases were scattered across the ocean floor like tiny islands of liquid water in a world of ice. The organisms that survived in these locations had to be incredibly hardy and adaptable. They lived in water that was often close to boiling, with high concentrations of sulfur and other chemicals that would be toxic to most life forms. These creatures developed specialized enzymes and cellular mechanisms that allowed them to thrive in conditions that would kill ordinary organisms. The volcanic activity that created these refuges also played a crucial role in eventually ending the Snowball Earth periods. Volcanoes continued to release carbon dioxide and other greenhouse gases into the atmosphere even when the planet was frozen. Over millions of years, these greenhouse gases accumulated in the atmosphere because there were no liquid oceans or active weathering processes to remove them. Eventually, the concentration of greenhouse gases became high enough to trap sufficient heat to begin melting the ice sheets. The melting process created some of the most dramatic climate changes in Earth's history. As the ice began to melt, dark ocean water and land surfaces became exposed, which absorbed more sunlight than the reflective ice had. This triggered rapid warming that caused more ice to melt, which exposed more dark surfaces, which caused even more warming. The planet went from completely frozen to extremely hot in a relatively short geological time period, with global average temperatures potentially reaching higher than 90 degrees Fahrenheit. The organisms that made it through the snowball periods had to restart ecosystems from scratch when the ice finally melted. They became the founding populations for the next phase of Earth's biological development. The genetic bottlenecks created by these extreme survival scenarios meant that the organisms that repopulated the planet after the ice melted had been selected for extreme adaptability and resilience. These freeze-thaw cycles actually accelerated evolution by forcing rapid adaptation to extreme environmental changes. The organisms that survived had to develop new strategies for dealing with temperature extremes, chemical changes, and resource scarcity. The evolutionary innovations that emerged during and after the snowball periods provided the biological toolkit that would be essential for later development. The harsh selective pressure of the frozen world eliminated organisms that couldn't adapt quickly, leaving behind lineages that were exceptionally good at surviving dramatic environmental changes. The survivors of this frozen apocalypse had been through the ultimate stress test, and they emerged with genetic flexibility that would prove essential when the next major challenge arrived. After billions of years of gradual change and catastrophic setbacks, life was about to do something completely unexpected. The Cambrian explosion's biological arms race. Evolution had been taking its time for billions of years, producing mostly single-celled organisms that lived quiet lives in the ocean. Then suddenly, about 538 million years ago, life decided to get creative and went from 0 to 60 in just 25 million years. This period became known as the Cambrian explosion, and it was basically nature's version of a nuclear arms race, except instead of building bombs, organisms were building claws, teeth, armor, and weapons that would make modern military engineers jealous. The Cambrian explosion marked the first time in Earth's history that animals started trying to eat each other on a regular basis. For billions of years, most life forms had been content to filter nutrients out of the water or absorb chemicals from their environment. They were essentially the ocean's equivalent of peaceful hippies, just floating around and minding their own business. But then some organisms developed the ability to hunt and kill other organisms for food. And suddenly, the ocean became a war zone where survival meant either being really good at eating things or being really good at not getting eaten. Fossil discoveries from 2025 research in China have revealed creatures so bizarre they look like alien designs that got rejected from a science fiction movie for being too weird. These Cambrian organisms combine body parts in ways that seem almost random, as if evolution was experimenting with every possible combination of biological features to see what would work. Scientists have found creatures with multiple sets of eyes arranged in patterns that make no sense by modern standards, along with tentacle arms that could bend in directions that would break the bones of any current animal. The peaceful filter feeders that had dominated the oceans for millions of years suddenly found themselves dealing with things that wanted to eat them. It was like going from living in a quiet neighborhood to suddenly having your house surrounded by armed predators. These organisms had to rapidly develop defense mechanisms or risk becoming extinct. Some grew hard shells that could protect their soft bodies from attack. Others developed the ability to burrow into sediment where predators couldn't reach them. A few species learned to move faster so they could escape when danger approached. The first eyes that evolved during this period created what scientists describe as an evolutionary surveillance state. Vision gave predators a massive advantage because they could spot prey from a distance and plan their attacks, but it also gave prey animals the ability to see predators coming and take evasive action. This led to an escalating arms race between better vision and better ways to avoid being seen. Some animals developed compound eyes that could detect movement from multiple directions simultaneously. Others evolved the ability to change color to blend in with their surroundings. Recent discoveries have revealed Cambrian creatures that push the boundaries of what we think of as possible animal designs. Scientists have found fossils of organisms with 5 eyes arranged in a pentagonal pattern around their heads, giving them nearly 360-degree vision. Other creatures had tentacle arms that could extend and retract like telescopes, allowing them to grab prey from surprising distances. Some had sideways mouths that opened perpendicular to their body axis, which seems like a design flaw until you realize it allowed them to process food while continuing to move forward. The diversity of body plans that emerged during the Cambrian period included designs that were so unusual they don't fit into any modern animal categories. There were creatures that looked like walking pineapples with legs, others that resembled mechanical robots with jointed appendages, and some that appeared to be biological experiments in combining features from multiple different animal types. Many of these experimental designs went extinct fairly quickly, but they show how rapidly evolution was testing new approaches to survival and reproduction. Research from 2025 has shown that this period essentially invented almost every major body plan that still exists in the modern world. The basic blueprints for arthropods, mollusks, chordates, and other major animal groups all appeared during this relatively brief window of time. Animals developed segmented bodies that could be specialized for different functions. They evolved jointed limbs that provided mobility and manipulation capabilities. They created internal cavity systems that allowed for more efficient organ organization. The development of hard shells and external skeletons during this period was revolutionary for both offense and defense. Shells provided protection from predators, but also created new opportunities for predators that could figure out how to break through them. This led to the evolution of crushing claws, drilling appendages, and other specialized tools for shell breaking. The arms race between shell makers and shell breakers drove rapid innovation in both protective and offensive capabilities. The question of why this explosion happened so suddenly after billions of years of relatively boring single-celled life has puzzled scientists for decades. The most likely explanation involves a combination of environmental changes and reaching critical thresholds in biological complexity. Oxygen levels in the atmosphere and oceans had been gradually increasing, and they may have reached a point where large, complex, multicellular organisms could finally get enough oxygen to support their metabolic needs. Another factor was probably the development of genetic control systems that could coordinate the activities of multiple cells. Single-celled organisms had been successful for billions of years, but they were limited in size and complexity. Once organisms figured out how to make different cells specialize for different functions and coordinate their activities, it opened up entirely new possibilities for size, shape, and capability. The Cambrian explosion also coincided with changes in ocean chemistry that made it easier for organisms to build shells and hard parts. The availability of calcium carbonate and other shell-building materials increased, which made protective armor more feasible for a wider range of organisms. This created new ecological niches for both shell builders and shell breakers, driving diversification in multiple directions simultaneously. The biological arms race that began during the Cambrian explosion established the template for every animal alive today, including humans. The competition between predators and prey drove the evolution of intelligence, complex sensory systems, and sophisticated behaviors that eventually led to the development of nervous systems capable of learning and adaptation. But all these evolutionary innovations and complex ecosystems that had taken millions of years to develop were about to face something that would make the previous mass extinctions look trivial by comparison.